Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello students, let us solve the next question, question number 9. Here it is question number 29 of JEE Advanced Physics Paper 2 2014 Code 8. So let us solve that question number 29. Hello students, let us solve question number 29. The question is a planet of radius r which is x by 10, that is 1/10 of the radius of Earth, 1/10 times the radius of Earth, has the same mass density as Earth. So there is a planet which is, suppose the planet is x. Here the radius of this planet Rx is or it says r, which is 1/10 the radius of Earth, 1/10 the radius of Earth, and has mass density same as Earth. So density of this mass density, this is same for this one and also for Earth. So if I consider Earth here, then density of Earth and density of this planet X, the density is same in both the case, but radius is different. Here it is r by 10 of Re. So if it is r, then this is 10r. So this is 10r and this is r. So, or in other sense, if I consider this as Re, then this will be Re by 10. Scientists dig a well of depth r by 5 on it. So on this r planet, this one, planet X, here the dig up to, this is our radius, so the dig well up to a distance of this, they dig a well, and that is r by 5. This distance is r by 5 from here to here. So they dig a well of depth r by 5 on it and lower a wire of the same length. That means now they put a wire here, lower the wire of same length. That means the length of the wire is same as this. This is the length of the wire. And of linear mass density, suppose that lambda, linear mass density of the wire, lambda is mass per length, that is 10⁻³ kilogram per meter. This is given 10⁻³ kilogram per meter into it. So this is the wire which is suspended from here. If the wire is not touching anywhere, so this wire is not touching anywhere, it is only suspended in the well and is not touching any part of the well. The force applied at the top of the wire, what is the force applied here at the top of the wire by a person holding it? So a person is holding it here. There is a person here who holds this wire, and how much force this wire the man has to apply, because if he lifts that it will fall down. So how much force the man has to apply? So that force is the force that is applied at the top of the wire by a person holding it. Radius of the Earth. Radius of the Earth is 6×10⁶ meter, and acceleration due to gravity of Earth you have to take 10 meter per second square. So for Earth, G is taken as 10 meter per second square, and the radius of the Earth, that is Re, is 6×10⁶ meter. So now we have to find the force applied at the top. That is basically the question is what is the weight of this wire. Whatever is the weight of the wire, that weight has to be applied here, because this has to be kept at equilibrium, so forces should be equal. The weight that is acting on this point on the wire has to be whatever is the force exerted by this earth on this wire, by this planet on the wire, that force has to be applied here by the man. So basically you have to find the weight of the wire in this planet X. Okay, so let us find the weight of the wire. Suppose this is the wire which is suspended in the cavity, and of length of this wire is r by 5. To hold it here, how much force is applied, we have to find the weight of the wire. To find the weight of the wire, because this is surrounded by Earth or the planet, and this planet center is suppose here. Now at each and every point on this, the force will be different, because we know that the acceleration due to gravity, as we move in a depth d, at any point inside, the value of z inside the depth, it is equal to g into 1 minus d by r, that is g into r minus d by r. This expression is known to us because this is a very known expression. The acceleration due to gravity at a depth d below the surface of the earth. That means if I go certain distance d below, this is the, if I go this distance below d, distance below, here the g is nothing but gd, and it is given by this expression. That means if I want to find the value of g over here or anywhere else, that g will be different, because that g varies with respect to this d, how far it is from. Now if I say that this is a center, if I concentrate on this point, then this point is at a distance how far from the center of the earth? If this is center of planet X, how far it is from the center of this planet, then this is r by if this is d, this is r minus d. This r minus d is nothing but the small r, we say. Small r is the point where we want to find the acceleration due to gravity from the center of the earth. So from the center of the earth, its distance is r. So from here I get gd equals to gr by r. So now gd is gr upon r, that means the acceleration due to gravity at any depth d below is proportional to r. That means it depends on the distance of the point from here. So if I consider earth, so from here also I can say that if this is the wire, then I consider at a distance r, I consider a small section of the wire of length dr. So at a distance r from here, I consider a strip of length dr. Then that strip is so small that the g, acceleration due to gravity, remains same during this length. So then if it is at a distance r, then I will write this as this only, and for this planet, this is in terms of the g of the surface of that planet, this is the G on the surface of that planet. Okay, this is the planet X, G on the planet X. G on the planet X are, this is on the surface, divided by R. I can write this as G naught R by X for the planet X. This is better way of writing. So in the planet X, at a distance d depth, the value of G is this. That is, G naught is the acceleration due to gravity on the surface. On the surface of this planet X. So therefore, I will write the weight of this portion of the wire. The weight of the portion dr of the wire is mass of that portion and G acting that point, G dx. Now this is the weight. The mass is lambda dr, because this is the linear density of the wire into dr, and this is gdx, which I got gdx as g naught r by r, g naught r over r. Okay, so at a distance, so I can see here the weight acting here is mass of this and what is the weight on this is this portion into g dx. This is the weight of that only, that portion. So I have to find I keep on finding the weight of each such strips over here. For each element I have to find the weight and add them. That will give you the total weight acting on this wire. That is done by integration from here to here. If this distance is r of this planet, if this distance is r and this is r by 5, because this is the wire length is r by 5, then this length will be from center to this, it will be r minus r by 5, that is 4r by 5, and from here to here this is r. So my integration will be from limit 4r by 5, because my elements will start from here and end here. So the limit of integration will be 4r by 5 to r, because my last element will be here. So the weight of the full portion of wire of length r by 5 is, that weight equals to integration of lambda dr g naught r divided by r. The limit varies from 4r by 5 to r. If it is the case, then I have to integrate this. The weight of the wire suspended is whatever is constant taken out, g naught is taken out. G naught is the acceleration on the surface of that planet divided by r, the radius of that, and lambda is also constant taken out. Inside it is r dr integration 4r by 5 to r. This is what we are getting. Now let us integrate that. Integration of r dr is r square divided by 2, and the limit of integration varies from 4r by 5 to r. Lambda g naught by r, and 2 comes out, no problem with that. If you put this value here, it is 16 by 25 r square minus r square. If I substitute the value of that, we'll get w equals to lambda g naught divided by 2r, that I got, and this calculation, this I have written and this I have to solve. This has to be this minus this, so it is the, this has to be upper limit minus lower limit. I have written the lower limit minus upper limit, so you take the mod of that. So you will get r square minus this. So it is r square minus 16 r square divided by 25. If you take that, then this is 25 minus 16, that is 9. This is 9 r square divided by 25. So it is 9 lambda g naught r square divided by 25 to the 50. So it is 50 r. 1 r cancels. So that comes out to be 9 by 50 lambda g naught r. This is the weight. Now if this is the weight, which is the wire that is suspended here, this wire has weight equal to, from anywhere, the center of gravity, the wire weight is 9 lambda g naught r divided by 50. Then if this is the weight, then that has to be the force applied at the top, because the person has to apply this much of force. That force must be equal to this. So force applied on top, force applied on top equals to weight of wire. So therefore force applied equals to this. So therefore force applied equals to 9 by 50 lambda g naught into r. Now for the planet, r is the radius, as I see the question here. The planet of radius r is re by 10. So this has radius r, and that is re by 10. Its density being same, radius is changing, and radius is changing, mass density is same. So now I have to find lambda is known and r is re by 10, and radius of earth is 10 raised to 16, 6 10 raised to 16. So radius of this planet equals to 6 10 raised to 6 divided by 10, that is 6 10 raised to 5 meter. This value will be put here. Lambda is known, only you have to find G naught. So let us find G naught before we substitute the value over here. G naught is what? The planet X, on the surface of that planet, the G is G naught we have taken. On the surface is G naught. But then that also we don't know. That we have to find, because that value is G naught, and inside that varies like that, ultimately we got whatever that result is. But then G naught on the surface of planet X must be related to the G on the surface of Earth. For any planet, we have a general formula for G, that G equals to Zm upon R square. This is the formula for any planet whose mass is m and radius is r. So if I talk about the surface of the planet, then I put the mass of that planet, r value of that planet, and G. But here, comparing with the Earth and the planet X, the mass is same, the mass density is same, so this mass has to be expressed in terms of density. If I express the mass in terms of density, it will be density into volume of the planet. It is a sphere of volume 4 by 3 pi r cube divided by r square. Because r square are already there, so if I cancel this, this becomes r. Only r. This is constant for any planet. This is constant for the given conditions. 4, 3 pi are constant. So I am getting G is proportional to R. G is proportional to R means now we have two situations, a planet Earth and a planet X. This is Earth and this is planet X. G proportional to R. G on the planet Earth is proportional to R on the radius of this planet Earth. G on the planet X is proportional to radius of that planet X. That means if I divide these two, I'll get G Earth by G on the planet X. Obviously on the surface equals to Rx. From here, so from here I am interested in the G on the surface of this planet, G naught on this planet X, that I am interested in G naught. Then G naught on planet X will become Rx upon Re into G on the planet X on the surface of that. Rx is given as R on the planet X is given as the 1/10 of the radius of the Earth. This is radius of the Earth is suppose that Re, then it is Re by 10. Rx is Re by 10, that is given into G on the surface of Earth planet. In the question you can see that on the surface of the planet Earth, the acceleration due to gravity is 10 on the surface. This is on the surface of the planet X. So this cancels and this is 10 divided by 10. This is 1 meter per second square. So I got ultimately G naught, which is 1 meter per second square, and I have to see that equation to get the substitute the value. I have this G naught I have to find. I got 1 meter per second square. R I have got 6 10 raised to 15 5 meter, and lambda I got as in the question given. This lambda is nothing but 10 raised to minus 3. So I have this is 10 raised to minus 3 kilogram per meter. I have to only substitute these values over here to get the value of force applied on the top of the wire suspended extending to the distance r by 2 on the planet X. The force applied on the top will be 9 over 50, and putting all this data, I'm just writing it. Lambda is 10 raised to minus 3, G naught is 1, and R is 6 10 raised to 5. This is the value I have to put. If I solve this, this is minus 4 and this is 5, this is 1 only. So it is 60 and 9 into 60 divided by 5. This much Newton. If I multiply 2 here and 2 there, then this becomes 10, and 10, this means this goes 0. This is 12 into 9 Newton. This is 108 Newton. If I see the option for this question number 29, then interestingly the option number 2 is 108 and our answer is also 108. So the option number 2 is correct. The force that the man applies at the top of this suspended wire has to be 108 Newton, because this is the weight of the wire pulled by this planet X is 108 Newton. This has to be balanced so that this wire can remain there. So answer is 108. Okay, thank you.